Vn. So this is the format of our equation. This is general format. In this we are using the complex values of x, c, r and this thing. If we want to find the magnitude of the output signal, only the magnitude of the output, then we will combine these things and we will use the value without j with this xc. So that will become xc divided by this thing. So this is actually the z. So z is equal to r plus xc in its complex values, or z is equal to r square plus xc square in its magnitude. So this is only the magnitude of that phasor, and z is again this thing. This is replaced in this equation. So we can write this equation as V out is equal to V in xc divided by z. Z is the total path resistance, so R xc. Okay, now what is xc? Xc is the impedance of the capacitor in terms of ohm. So xc is 1 over omega c, and omega is 2 pi f. So omega is replaced as 2 pi f and c is written, and this gives us our xc. So now we have all the values for our equation, so we can find the V out at any frequency. Say we are having a range of frequencies from 1 Hz to 100 to 1000 to 10,000. We put this in this equation and then in this equation, and then we put this and this and this as our f. We calculate xc for 100, 1000 and 10,000. So we calculate xc and then we put this xc in this equation, and we find this voltage. So if we draw this equation, it will be something like this. This thing will be decreasing. Why? Because at higher frequencies the voltage will be attenuated. So this will give us our physical filter structure in terms of frequency axis and the magnitude of signal as V out. Okay, there is an example on this low pass filter. The low pass filter circuit consists of a 47k ohm resistance. Sorry, this thing is a bit wrong, let me correct it. So this is a 47 k ohm in series with a 47 nanofarad capacitor, which are connected across a 10 volt sinusoid supply. So this is a 10 volt supply, and calculate the output voltage at frequency 100 and again at frequency 10,000, and this thing, this is OR. Okay, so this is our example that we have to calculate the output at 110k hertz of frequency. So for that we will calculate the XC100 and XC10k. So how did we calculate that? For that, let's check first that what is this output. This output is the component of this input. We can calculate this output by dividing this XC divided by R plus XC and then multiplying by Vn. So this is our V out. Now this is in phasor in magnitude form, so square as well. Okay, now calculate XC 100. So for that we will use XC is equal to 1 over 2 pi f c, and f is 100 here. C is how much? C is 47 nano. So if you put these values in it, 47 nano multiplied by 100 multiplied by 2 pi and whole inverse 1 hour, and we get this 33.8 k ohm. So this is our XC. Now we can calculate our V out. So V out would be 10 volts multiplied by XC divided by resistance square and XC square. So resistance is 47k. So this is not 47k. This is 4.7k as we see in here. I was thinking that how can this thing be wrong. Okay, so this is 4.7k, and this nomenclature was, I guess, used in the lab as well, that 4k7 ohm, 4k7 ohm. So this was 4.7k ohm as written in here. Okay, so we can also write it like this. So 3700 ohm would be written as 3k7 ohm. Okay, this was a general information just because we had some doubts in it. Okay, so we put this for 700 square and 33863 square, and we got 9.9 volts. So the input voltage is 10 and the output voltage is 9.9 volt, which is almost equal to 10. If you want to calculate the gain in terms of voltage, what will we do? We will write 20 log output by input, 9.9 divided by 10. So this turns out to be 20 log of 0.99, which is almost equal to 0. So say minus 0.9. Yes, so this is like, I don't know what will be the value of it, but this log will be negative dBs. It will be less than 0. So minus 99 or minus 0.1 or something else. Just calculate it. Okay, now we repeat the same process for XC equal to 10k. So at 10k we first put 10k as frequency and 47 nano. Nano is 10 power minus 9 if you don't know. So we put this thing in it and we found 33.6 as our XC. If we calculate the output now, output would be 10 multiplied by 338 divided by 338 square plus same resistance square. So this gives us an output of 0.7. So first it was 9 and now it is 0.7. It is even lesser than 1. So the gain would be 20 log 0.7 divided by 10, which is 20 log of 0.07. So here it was 0.9 and it was 0.0. So this is very much lower in negative values of dBs. So this is what happens if we increase the frequency. So this clearly says that the SAD filter, this filter that we are discussing, is a low pass filter. It allowed 100 Hz, but it didn't allow 10k Hz. The frequency response of this low pass filter is a bit easy now. It will be studied with the data from the previous example. So we can see from the result that the frequency when it was 100 Hz, the response was good, but when it becomes 10k, the response was bad. So that means that it was a low pass filter. The band that was passed was in that example is here, By plotting the network's output voltage against different values of input frequency, the frequency response curves or bode can be found, which is shown like this. We can also find the phase of this same filter. What is phase? Phase is the angle which is being observed by the output when it goes through the circuit. So first the circuit was resistive because the capacitor was not acting. The circuit was resistive because all the voltage was forwarded through the resistor from input to the output. So this will show us a zero angle, which is shown in here. As the frequency increases, the capacitor starts its working and the circuit becomes capacitive at higher frequency. So all the voltage is being grounded. And capacitor is 1 over j omega c. So this will give us a minus 90 degree with the output voltage. So when we increase the frequency, the voltage angle, if we check the voltage in here, it will have a minus 90 degree angle with it. So after the cutoff frequency, we see that the circuit is having a phase shift of 90 degrees. So this happens at very high frequency. At lower frequency we get 45 degrees and greater than 45 degrees, but not this 90 degree. 90 degree is at infinity, theoretically. What is this cutoff frequency? Cutoff frequency is the knee of the graph at which the circuit starts attenuating its output, and it gives output of 70% of the input. So 70.7% of the output is at 45 degree. So this condition is known as the cutoff frequency voltage. 45 degree is actually the halfway between 0 degree and 90 degree. So we can also call it the half power bandwidth. So half power bandwidth is observed at cutoff frequency. So cutoff frequency हम किस तरह define करेंगे? Xc is equal to R and 1 over 2 pi Fc is equal to R. Now separate this F. 1 over 2 pi Cr is equal to F. So this is our cutoff frequency. For the same circuit that we discussed, the cutoff frequency is at 720 Hertz. How we calculated that? We had 4K7 ohm resistance and 47 nano capacitance, and we put that in this equation for Fc, and we got 720. So at 720 we will get a 45 degree phase, and we will have half the voltage of 70.7%. So 70.7% is actually 1 over under root 2, and 1 over under root 2 in logarithmic scale is the 3 dB. So 3 dB bandwidth, half power bandwidth, or 1 over under root 2, which is 1 over 707. So this 0.707, you might be familiar with it. So this is what happens if we increase the frequency, that the change in phase as well as voltage occurs. Check this thing by yourself, that what is cutoff frequency, what is half power bandwidth, and why we use 45 degree as our half power. Okay, now going towards some higher order low pass filter. Second order filter will be a cascaded version of the series version of the low pass discussed filter. This is similar structure, but we are combining two circuits. This is first stage, this is first stage, filter and this is second stage filter. So we will get double attenuation due to this. So if we had a 20 dB per decade loss by the previous filter, now we will have 40 dB per decade loss in the signal after cutoff frequency. So this is termed by this equation, that number of series filters multiplied by 20 dB will be our combined loss or gain. Okay, so there is more than one RC network, that's why it is known as the nth order for such case, and n is equal to 2, so this gives us a second order low pass filter. Also we can calculate its corner frequency or the cutoff frequency as 1 over 2 pi R1 C1 R2 C2. So this equation is now modified. We are multiplying the capacitances and resistances for 2 times because we had 2 circuits now. Also the second order low pass filter 3 dB frequency, which is that 3 dB gain which we discussed, can be found by Fc 1 over 2 power 1 over 2 minus 1. So these are the equations that you should probably be remembering by yourself. Okay, and passive low pass filter gain is 1 over under root. So for the first filter it was 1 over 2, but now it is whole n. N is 2 here because these are 2 filters. It can be 2, 3, 4, 5 for nth order. So this is the low pass second order filter. Let's discuss its graph. The first filter which we had previously had this 3 dB graph, and the second one is also having a 3 dB graph, but the loss is now 20 dB per decade converted to 40 dB per decade. So first filter had this knee here, the second will be having the knee here. So this is our FC for the second, this is the FC for the second. Here are some of the things increased. So if these things are increased, this will lower this frequency, bigger denominator, lower FC. So first we had 1 over 2 pi 2 pi RC. So 2 pi RC was bigger than 2 pi R1 C1 R2 C2. So that's why the first one is here and the second one is here. So this is a bit lower FC2 for the second. Okay, and the gain is converted to 4 minus 4 dB, 40 dB, because the graph is now more steeper. It is not like this, it is like this. So this is the frequency response of second order filter. We use filters in pulse shaping. If we have such inputs, let's say a very steep increase in the voltage, and we pass it through a resistor, what will happen? This resistor will make it a bit linear, and if we pass it through a capacitor, what will happen? It will integrate these things. It will start from here and will add up all the voltages up to here. So integrator can be formed by a simple low pass filter as it decreases the high frequencies. So high frequencies are decreased and lower frequencies are remained, which make this thing a sawtooth wave. Not a sawtooth wave, but a triangular wave. So this is a triangular wave now. So this is a phenomena which can be observed by taking a square wave at the input and using a low pass filter. What will we get? We will get this wave. The high pass filters. High pass filters allow high frequency and do not allow the low frequency. So as the name suggests, this high pass filter will work totally opposite to the one that we discussed. So this is the structure of the high pass filter. At high frequency the capacitor becomes short, and at low frequency it becomes open and do not allow the signal to pass. So if we have, let's say, a frequency band, at low frequency it will not